In part 1, we have derived the relationship between the stress and the curvature rho. So as we know, the stress can be expressed, we can find an expression for stress by using the moment, internal moment. So then we can find the relationship between the moment and the curvature. So, but before we find to derive this relationship, and I would like to see the deformation due to the external loading is come from two parts. So one part is bending deflection. The other part is shear deflection, is a deflection due to shear force. But here we only consider the deflection due to the bending, because in most of the time the shear deflection is very small compared to bending deflection. So it is negligible in most of the time. So here we only consider the deflection due to bending. So we call this pure bending. So here we have a beam segment and two bending moment. So this bending moment is positive based on the sign convention. We call this pure bending. So for pure bending, so if we have if we look at a section here, so if we look at a section here, so as we know, we have a line, we have axis is we call the neutral axis. So I write down here neutral axis NA here. So if you look at the section here, so above neutral section, the part of this beam will be shortened, will be in compression. So there's a compressive stress on the top part. Similarly, the bottom part there is in tension, so there's a tensile stress. So if we draw so we have compression stress, we have tensile stress. So this is stress. So this is the section. So if we look the cross section area, if this cross section is a rectangular cross section, so we can draw the distribution of this stress. So above this neutral surface or neutral axis, neutral surface, that is compressive stress. Below the neutral surface is tensile stress. So as you know, this stress distribution will create some moment. So we'll create some moment. If we say the moment is m, so we can express the moment by using this stress distribution. So how can we do how could we do that? So here okay. So first we can build up coordination systems. So here coordinate systems, we have vertical axis y and horizontal along this neutral surface is z, and this is 3D, so x-axis. So this is 3D coordination system. So now if we look at this cross section in 2D dimension, in 2D, so we can draw the cross section like this. So it's a rectangular, so but rectangular surface, rectangular cross section. So we can build the coordination system is y and z. So this is cross section. So we know along this cross section there is compressive stress and tensile stress. So how could we express this? How could we find out the bending moment is due to this stress? So we're going to do like this. So first of all, we find arbitrarily we find a small area dA. So small area dA, which shown here, small area dA. So this small area have a distance from the axis, from the neutral surface or neutral axis is y. So the distance is y. So there is some stress on this small area. So if this area is very small, so we can assume the stress is constant. There's no change on the stress. It's constant. So we say it's rho. So the resultant force on this small area will be rho times dA. dA is the area. So this resultant force have a bending moment, have a moment along this neutral surface. So the moment will be the force times the lever arm. Lever arm is y. So this is the bending moment due to this small area. We say this is dm equal to the stress. So this is not, so here stress we expressed by using sigma. So it's not rho. So sigma dot sigma, the area and the lever arm. So but here that's something we need to be careful about here. So here the stress is compressive stress. Compressive stress is go to the negative direction of x-axis, so it's negative, and dA is a constant positive. So y here is positive. So positive, negative. So this term is a negative value. But dm the direction is go for like this. So it go for counterclockwise. So counterclockwise, if we see the diagram here, so this is positive. So we say based on sign convention, we draw the positive bending moment like this. All the bending moment is positive on this beam segment. So this is positive bending moment. So dm is positive, but this term is negative. So we must have a negative sign over here. So to make this term is positive. So now we have expression for a very small area. The bending moment come from very small area. So if we want to know the bending moment due to the whole cross section, so then we need to using the area integration. So we will have in total the bending moment is the area integration is dm. So this is the total bending moment on this cross section. So if we write down is minus sigma dA times y. So we have derived the sigma stress is equal to minus EY over rho. So if we plug in the expression for sigma, then we will have I write down over here. So is minus, okay, so sigma is EY over rho. Rho is the radius of curvature, and dA times y. Okay. So if we simplify it, rearrange this integration, we will have the area integration EY of rho y squared, so y times y is y squared dA. Okay. So in most of the time, the E and rho is the same over the beam, so we can put E and rho outside of this integration. So we will have E rho area integration y squared and dA. So look at these terms. Remember that we have defined the moment of inertia. Moment of inertia is I equal to y squared dA. So this is a moment of inertia. Also, you call this is a second moment of area. So this moment inertia. So we can reduce this term with EI rho. So now we have the expression. We have a relationship between bending moment and curvature. So the procedure is that we start from a small area, then we're using area integration to derive the relationship between the moment and the curvature. So after we have these relationships, and we can go further. Then we can go further to find a useful equation to help us to find out the deflections. So as we know, the radius of curvature in calculus, we have derived the radius of curvature can be expressed in by, so this is a radius of curvature. So 1 over radius of curvature is equal to d square y dx square over a very complex term. So 1 plus dy over dx, so square times, so square 3 over 2. So this is the exact expression for the radius of curvature. So this is very, so we can use in this we can use this term to find the relationship between the bending moment and the y. Y is a deflection, but this one is a little bit complex, and as we know, most of the time our deformation is quite small. So it's quite small. Then this term is very small. It is negligible. So then we can cancel this term. So then this term is equal to 1. So approximately 1 over rho is equal to d square y, and dx square. So after we use this approximation, we can express this equation with this new term d square y and dx square. So if we rearrange this term, we will have d square y and dx square equal to m over ea. M over ea. So we just put m over ei. So we just put ei to the left-hand side. So this equation is we call elastic beam theory. So this differential equation will help us to find out the slope of the beam curve and the deflection of a beam deformation. So we will talk about it in the double integration method. So that's it. Thank you.